Hi everybody, welcome to Day 6, Section 7.5, Operations with Radical Expressions. So today we are going to be simplifying radicals. Some of it's going to be review and some of it is going to be new. So along with that, we're going to be adding, subtracting, and multiplying radicals. All right, so let's go ahead and get to it. The first couple examples we are going to be reviewing. So let's go ahead and recall how to simplify the following radicals. The square root of 20, okay, the square root. So what we're looking for is the biggest perfect square that goes into 20, okay? And we should all recognize that the biggest perfect square that goes into 20 is going to be 4, all right? So 4 times 5 gives us 20, and the square root of 4 just becomes 2, and we are left with root 5 underneath our radical. All right, so that aspect should be review. However, if we can't come up with the biggest perfect square, we can do our jailbreak method looking at the prime factors of 20. So a little side note, I can take 20, and since 20 is even, I'm going to divide by 2. And 2 times 10 is 20. 10 is still even, so I divide that by 2, and I get 5. And since I want the square root, I want groups of 2's. All right, well, sorry. I want groups of 2 numbers, 2 of the same number. And in this case, it happens that I have one group of 2 2's. All right, so a 2 would come out in front of the radical, and whatever numbers are left stay underneath our radical. All right, so we would get 2 root 5. Okay, so that's just a quick reminder of simplifying square roots. All right, so quickly looking at the square root of 96, we could go ahead and say, all right, well, let's look at the biggest perfect square that goes into 96. And maybe we recognize right away that the biggest perfect square that goes into 96 is 16, and it goes into 96 6 times. The square root of 16 we get is 4, and we're left with the square root of 6 underneath our radical. Well, 6 underneath our radical. Okay? Now, if we didn't recognize that, we do our jailbreak method. We take 96. 96 is even, so we divide it by 2. 2 and 48. 48 is even, so we still divide by 2, and we get 24. 24 is even, 2 and 12. 12 is even, 2 and 6. 6 is even, 2 and 3. Okay, so again, we're looking for pairs of numbers. All right, so here is one pair of 2's. Here's another pair of 2's. So when I pull this first pair out, I write it as a 2. I've got another pair. I write that 2, and no other pairs remain. So I just multiply these 2 numbers together, and that stays underneath our radical. So 2 times 3 is 6, and then I simplify the coefficient. 2 times 2 gives us 4 root 6. Obviously, this is a tedious process, so it helps to know your perfect squares to go about it the initial route I told you. Okay, so hopefully that was a quick review. But now we're going to get into some new notation. All right, we're going to be dealing with different roots, not just square roots. We're going to look at cube roots and fourth roots, etc. So now what we're going to look at is this little side note to the right over here. Okay, so we have the nth root of a. All right, the nth root of a, where n represents the index, and it's a smaller number really close to the radical, and a is known as the radicand. It's the value underneath the radical. Right? If you take a look at the first 2 examples here, the square root of 20 and the square root of 96, we should notice that there is no n. The index is not written in. So when there is no index written, it's assumed to be 2. Okay, so make sure you make that note. All right? Okay, so let's take a look at our first example. All right? what if the radical isn't a square root this time? Okay, so now we need to start knowing our perfect powers. Powers of 3, powers of 4, powers of 5. And we need to introduce ourselves to those because it makes our life a lot easier. Okay, so in part A, the cubed root of 48. Now I want the biggest power of 3 that goes into 48. So 2 cubed, 3 cubed, 4 cubed, you need to know those powers. It just so happens that the cubed root of 48, the biggest perfect third power that goes into it, is 8. And 8 goes into 48 not 16 times, 6 times. All right, and now we simplify it very similarly to how we simplified the square root up above. So the cubed root of 8 is 2. And we're left with the cubed root of 6. So our answer is 2 times the cubed root of 6. All right, now, just like up above, we can do the jailbreak method. All right, so if we're doing the jailbreak method, we've got 48. And I go about it the same way. If it's even, I divide by 2, and it's even. So 24. 24 is even. 2 and 12. 12 is 2 and 6. And then we've got 2 and 3. Only this time, our index tells us how many numbers we need as a triple this time. Okay, so now we need groups of 3 numbers, 3 of the same. So we take a look. Okay, well, we've got one group of the same number, 3 of the same number, and that's as good as it's going to get. So we pull a 2 out, all right, and the rest of the numbers I multiply together, and that's what stays underneath our radical. Okay, so it's a little bit different there. All right, let's take a look at the next example. But before we go ahead and get started, I am going to erase some of this work here so that we can... Oh, maybe I won't. Okay, well, I'm going to change this example. What I want us to now do is I want us to really take the 4th root of 243. Okay, so now we need to know our perfect powers of 4. What's the biggest perfect power of 4 that goes into 243? Well, if you know your perfect powers, it makes our lives a lot easier. And we should be able to say, oh, well, I know that 81 is a perfect power of 4, and that times 3 gives me 243. So the 4th root of 81 is 3, and I'd be left with the 4th root of 3 underneath. Okay? But right now, if we don't know our perfect powers, which we should, we can do the jailbreak method. Okay? So a little side note. I take 243. Now, 243 isn't even, so I can't divide it by 2. So the next prime number I try is 3, and it so happens that 243 is divisible by 3, so 3 times 81. 81, not even, so I have to try my next prime number, and that would be 3. 3 goes into 81 27 times. I can break 27 up into 3 times 9. And 9 as 3 times 3. Take a look at your index. Your index tells you how many need to be in the group, how many numbers need to be in the group. Well, this time, I need 4 of the same number. Our index is a 4. So, do we have a group of 4 of the same number? Yes, we do. We've got 4 3s. So a 3 will come out, and the value that's left underneath the value that's left alone stays underneath our radical, and that should be a 4th root. So 3 times the 4th root of 3 would be our final answer. Okay? So, as I mentioned, it helps to know your perfect powers. All right, it's going to make our lives a lot easier. Okay, now what if there are variables underneath the radical? What do we do then? All right, well, let's see. Okay, so the square root of x to the 4th power. A nice way I like to go about this is I like to think about it as whatever my power is of my variable, I divide that by the index. Okay, so if I want to look at x to the 4th and simplify the square root of x to the 4th, I take the power, 4, I divide it by our index. Now I don't see an index, it's the square root. What's the index if it's not written in? The index is 2, all right? So 2 goes into 4 how many times? Well, it goes into it 2 times with a remainder of 0, okay? So what does this mean? Well, that 2, that first number, that becomes the power on the outside. All right, what does that mean? Well, it means when I rewrite x outside of the radical, that 2 is the power, okay? The remainder, that becomes the power of what remains inside the radical. Okay, so it'd be x to the 0 power would remain. So we'd have the square root of x to the 0. Well, anything raised to the 0 power is just 1, and the square root of 1 is 1. So our final answer here is just x squared. Okay, this comes into handy when we start dealing with different indexes. All right, so let's take a look at D, the cubed root of x to the 7th. All right, so when we're simplifying the cubed root of x to the 7th, I take my power, 7, we divide it by the index, 3. 3 goes into 7 2 times with a remainder of 1. So what comes out? Well, an x to the 2nd comes outside of the radical, and then we're left with the cubed root of x to the 1st power, or just x. Okay, so our final answer here would be x squared times the cubed root of x. Okay, and then finally example E. Now we've got multiple variables, so we just have to do our little side note a few times. So to simplify our x to the 6th, we take 6, we divide it by our index. Remember, if our index isn't written in, it's a 2. 2 goes into 6 3 times with a remainder of 0. All right. For y, we have y to the 9th. 9 divided by our index, 2. 2 goes into 9 4 times with a remainder of 1. And then z to the 1st power. Well, it's our power divided by our index, 2. Well, 2 doesn't go into 1, so it goes into it 0 times with a remainder of 1. So our final answer, well, let's see, how many x's come out? Well, an x to the 3rd comes out. All right, and what stays underneath the radical? No x's remain. A y to the 4th power comes out, and 1y stays underneath. And let's see, no z's come out, but 1z remains underneath the radical. All right, so our final answer, x cubed times y to the 4th times the square root of y times z. Okay, and now we're going to throw them all together. So what if there are numbers and variables underneath the radical? Well, let's see what we get. Okay, so I do my side note. The square root of 32. Well, we should be able to say that that is 4 root 2. X to the 5th. Take 5, divide it by our index of 2. We get 2 with a remainder of 1. For y to the 7th, We take our power, divide it by our index. We get 3 with a remainder of 1. So cleaning up our final answer, we have a 4 on the outside, a root 2 underneath so far. We have 2 x's that come out and 1 remains underneath the radical. We have a y to the third that comes out and 1 y that remains underneath. And there we have it. Okay? Next, now it's the cube root of 27x to the 10th. So the cubed root of 27, well, if we know our perfect powers, we know that that's just 3. X to the 10th, 10 divided by your index, 3. 3 goes into 10 3 times with a remainder of 1. So our answer, a 3 comes out, and x to the third comes out, and the cubed root of x remains underneath. Okay? Finally, the fourth root of 48 times d to the fourth times e to the 9th times f to the 14th. So let's do our side notes. The fourth root of 48. Again, knowing your perfect powers. Your perfect powers of 4. Well, the biggest power of 4 that goes into 48 is 16. The fourth root of 16 is 2. All right, with the fourth root of 3 remaining. For our d's, we take our power, divide it by our index. We get 1 with a remainder of 0. For e, we take 9, divide it by our index. We get 2 with a remainder of 1. And f, we take our power, 14, divided by our index. We get 3, remainder 2. So our final answer, a 2 comes out, and what's left underneath? The fourth root of 3. 1d comes out, none remain. E squared comes out, 1e remains, and f to the third comes out, and f squared remains underneath the radical. Okay, so I know these notes are taking a while. We still have one more page to go, but there's a lot involved with these. And the quicker we know our powers, the better off we'll be. So let's go on to the next page. Okay, so now we're going to focus on adding and subtracting radicals. So the key here is when we're adding and subtracting radicals, we need to keep in mind a few things. Step number 1 is we need to simplify each radical. All right, so simplify each radical. After that, we focus on the coefficients and we add or we subtract the coefficients of like terms. Of like terms. There we go. Okay, so what are like terms when we're talking about radicals? So in order for radicals to have like terms, they must have the same index and the same radicand, so the same value underneath the radical. Right? If those two things are not identical, they are not like terms and we cannot combine them. Okay? So let's focus on these first few examples. All right, let's focus on example A, where we have the square root of 6 plus the square root of 6. The first thing we want to zoom in on is the first radical, the square root of 6. Can we simplify the square root of 6, honey? No. All right, and now we double check. Do both of these radicals have the same index? The answer is yes. And what is their index? Well, since it's not written in, their index is 2. Okay, and now we focus on their coefficients. So the coefficient of this first radical, 6, is 1, and the second is also 1. So now we're just zooming in and we're adding their coefficients. So 1 plus 1 is 2, and then I keep the root 6. So our final answer is 2 root 6. Okay, with part B, again, we take a look at the radicals. Square root of 7 can't be simplified. And I check their index. They both have an index of 2. And now we zoom in on the coefficients. 4 minus 8 is negative 4. And we keep the root 7. Okay? Taking a look at example C. 2 times the 4th root of 3 plus 4 times the cubed root of 3. All right, look at the radicals. The 4th root of 3 cannot be simplified any further. Neither can the cubed root of 3. Okay, now the radicands are the same. They each have a 3 and a 3, but notice the index is different. One's a 4 and one is a 3. Therefore, we cannot combine these any. And the best we've got is 2 times the 4th root of 3 plus 4 times the cubed root of 3. We cannot simplify any further. Okay? All right, let's take a look at these next couple of examples. And we'll go from there. So, part D. Now it is the cubed root of 32 plus 2 times the cubed root of 500. And this is where your perfect powers come into play. All right, so we need to know the biggest perfect cube that goes into 32. We need to simplify both of these radicals. So, if you know your perfect powers of 3, you should know that 8 is the biggest power of 3 that goes into 32 evenly, and it's 8 times 4. Okay, plus 2 times the cubed root. Well, what's the biggest perfect cube that goes into 500? Well, that's going to be 125. 5 times 5 times 5. And 125 times 4 gives us 500. So now we're going to take the cubed root of 8, and we get 2 cube roots of 4 plus 2 times the cubed root of 125 is 5, and we are left with the cubed root of 4. Now let's just clean up our coefficients before we do any combining of terms. So this first term stays 2 times the cubed root of 4. The second term, we're going to have 2 times 5, which gives us 10 times the cubed root of 4. Now we double check. Are the indexes the same? They're both 3's, so that works out. And are the radicands the same? They absolutely are. So now we can combine our coefficients, 2 plus 10, for a grand total of 12 times the cubed root of 4. Okay? All right, now I want you to pause the video and try example E on your own. And when you're done, come back and see how you did. Okay, hopefully you had a chance to try part E, and what you should have gotten was a grand total of 11 times the square root of 3. All right, if you did not get that, or you struggled with that example or any of these, make sure you ask your teacher tomorrow. Okay, and finally, moving on to the very last example of this lecture is talking about multiplying radicals. Okay, so the rule of thumb when multiplying radicals, we multiply the coefficients then the radicands, and then we simplify from there. Okay? And another rule is they have to have the same index in order to multiply the radicands or these radicals at all. Okay? So, zooming in on example A here. All right? First thing I'm going to focus on is my coefficients, 2 and 4. Okay, so we're going to multiply 2 times 4. And I'll just write it as 2 times 4 for now. And now we can multiply the radicands. So the cubed root, and I like to put all my numbers together. So 9 times 6, x squared times x, y times y6, y to the 6th. Now you could go ahead and combine these all in one line of work. I'm just kind of showing you what it's going to look like. So now if we clean it up, we've got a coefficient of 8 times the cubed root. 9 times 6 gives us 54. X squared times x. Remember, we add the exponents. We get x cubed. Y times y to the 6th will give us y to the 7th. And now we can do our side note in order to simplify. So focusing on the cubed root of 54, the biggest perfect power of 3 that goes into 54 is 27. And the cubed root of 27 is 3, leaving us with the cubed root of 2. Okay, so 54 is really 27 times 2. Okay, now with our x's, we've got x cubed, and remember from the previous page, we take our power, we divide it by our index, and 3 goes into 3 one time with the remainder of 0. So 1x comes out and 0 remain. And then our y to the 7th, we take our power, we divide by 3. 3 goes into 7 2 times with a remainder of 1. So 2 y's are going to come out front and 1 y is going to remain underneath. Okay, so cleaning everything up, we still have this 8 out front. We're going to multiply it by this 3 that we got. Okay, and what remains underneath the radical? So the cubed root, we start with a 2. All right, the number of x's that come out, we take a look. 1x comes out, and 0 x's remain. And for our y's, we get 2 y's come out, so y squared, and then 1 y remains underneath, so y underneath there. And now we just clean anything up for our coefficients. So 8 times 3 is going to give us 24x times y squared times the cubed root of 2y. And there is our final answer. And that ends these long notes. So we are finally done. I know there was a lot involved with this lecture. So if you have questions, make sure you come to class tomorrow with them. Okay? Have a nice night. Bye-bye.